Okay, this is lesson 6.6, and in this lesson we're going to select a regression model. Until now, every time we did regression, I told you which model to use. Today we're going to do a question by hand and a question on Desmos where we're going to decide which model we should use. And the way we can do that is, well, first we can compare the first and second differences with the growth or decay rate, the Y ratios, and we can make a decision based off of that. Secondly, what we could do is we could graph the data and look to see whether or not it looks like a line, a curve, or specifically a parabola. Finally, we can look at the R squared value using the regression models, and that's actually what we're going to lead into with our last example. We're going to compare R squared values to decide. And in our first value, we're going to just look at first, second differences and Y ratio and then make a decision. So here we go. Electrical appliances such as a VCR or digital clock, this is dated, contain a capacitor for power during brief electrical outages. The table shows how voltage in the capacitor decreases over time after a power outage. Which type of relationship seems to exist between voltage and time? Justify your answer. Well, let's compare first, second, and Y ratio. First differences. We're going to look at consecutive Y values. We're going to subtract. 7 minus 9 is negative 2. 5.2 minus 7 is minus 1.8. 3.9 minus 5.2 is minus 1.3. Down 0.9 in our next one, and down 0.7 in our last one. So as you can see, first differences are not the same. So this doesn't look like it's linear. Second differences. Between these two, we're going up 0.2. This one's 0.5. This one's 0.4. And this one's 0.2. Well, our second differences aren't the same either. So this is not quadratic. So we're expecting maybe this is going to be exponential. So let's look at the Y ratio. Refresher, how do we do Y ratio? We divide consecutive Y values. So 7 divided by 9, and then we're going to do 5.2 divided by 7, then 3.9 divided by 5.2, then 3.0 divided by 3.9, and then 2.3 divided by 3.0. And let's see what we get. 7 divided by 9 is 7 over 9. 0.7 repeating. So let's go 0.78. And then 5.2 divided by 7 is 0.74. And then 3.9 divided by 5.2 is 0.75. 3 divided by 3.9 is 0.77. In our last one, 2.3 divided by 3 is 0.766, so call it 77. So the Y ratios aren't the same either. So we don't have a perfect match for a line, a parabola, or an exponential curve. But what we can do is we can pick the best model. So which one's closest? Well, 0.2, 0.5, 0.4, and 0.2 are a little off. If we rounded these all to one decimal place, this would be 0.8, 0.7, 0.8, 0.8, 0.8. Those are pretty close. So what we could conclude is we could say because the Y ratio is closest to being constant, the best model is exponential. It's not a perfect model, it's just the best model because it's the one that's closest to fitting. So it's like the curve of best fit rather than the perfect curve. All right, let's flip it over. Now we're going to use Desmos to decide. So we can ignore a couple instructions on this page because we are using Desmos. So we don't need the graphing pointers and we don't really need to draw a sketch. We're just going to compare the linear, quadratic, and exponential models. And our example is, in a science experiment, students punched a hole near the bottom of a 2-liter pop bottle. They filled the bottle with water and measured how the water level changed over time. Results are shown in the table below. So time in seconds and where the water level is in the table, or in the water bottle. So let's get Desmos up and running, and we'll look to decide what model is best. Okay, we got Desmos up here. We're going to compare linear, quadratic, and exponential. First, we need to put our table in Desmos. So plus sign table, and we've got x1 is 0, and then 25, and then 50, 75, 100. And for our y's, we've got 30, 22.3, 16.1, 11.2, and 7.8. All right, and now we got some points. Let's zoom out, see if we can find those points. There they are. Oh. All right, that's not bad. Could be a line, could be part of a parabola, also could be part of a curve. Could be any model just from the picture. I'm going to change the scale a little bit. Let's change our y scale. So let's look between, say, -5, so just below 0. And it looks like the biggest number in the table is 30. So let's go 40. Get a little bit more shape to the curve. If it is a curve, looks like a curve. All right, it's probably not a line. Let's use some regression to decide. If we remember, linear regression looks like this. y1, squiggly line, mx1 plus b. Quadratic looks like y1, squiggly line, ax1 squared plus bx1 plus c. And exponential looks like y1 squiggly line, a b x1 exponent. So what we're going to do is we're going to type all three of these equations in at once on Desmos and then look at our r-squared values. So we've got y1, and we got squiggly line, mx1 plus b, and now we can see our line of best fit and our r-squared value right here, 0.9778. So I'm going to add that, 0.9778, which is a really high r-squared value. Remember, the highest number is 1. Let's try quadratic. y1, squiggly line, ax1, and we want this one to be squared, so we got to use our squared, plus bx1 plus c. And there we've got our r squared. Wow, look at that. R squared of 1. Looks like this model is quadratic. Now there is a chance the exponential model can fit. Correction, there is not a chance the exponential model can fit as well. But let's type it in for completeness. y1, we want squiggly line, a, b, and exponent x1. And let's change the color. Can we change the color? Yes, we can. We want another red one. Let's make it purple. There we go. Done. All right, there we got all three of our regressions on there. We got our purple exponential, our black quadratic, and our red linear. And ooh, look at how close that is. That r squared for our exponential right here, 0.9981. So if we take a look here, the r squared that's the highest is our quadratic model. So if we were to select the best model, we're going to pick the quadratic because that's the highest r squared value. So which model best represents the data? We would say quadratic. And it's because the r squared value was 1, which means the parabola of best fit goes through all points perfectly. Determine the height of the hole in the bottle. Justify your answer. It says hint, use the trace minimum feature. We don't have that on Desmos. But if we remember water's draining out of the bottle, eventually that hole is going to hit and it's not going to drain anymore. So it's going to be the minimum. So I'm going to turn off these other models. Just got our parabola on there. And we're going to go look for the minimum. And there it is right there. So at 148.1 seconds, there's only 5.176 centimeters of water. So let's say that. Determine the height of the hole. So that's the centimeters. So the height of the hole is 5.176 centimeters. And that is because that's the minimum value. All right, that's it for lesson 6.6, and in fact, that's it for unit 6. Thanks for watching, and I'll see you in unit 7/8.